Welcome to Module 5 on quadratic equations. In the last module, we looked at factoring as well as factoring quadratic expressions. In this set of notes, we're going to look at solving quadratic equations. The general form of the quadratic equation is given by f of x is equal to a times x squared plus bx plus c. Note there's a requirement for a to not equal 0, as if our coefficient a was equal to 0, we would be left with a linear equation and not a quadratic equation. We often look to solve for ax squared plus bx plus c is equal to 0. In other words, we set f of x equal to 0, and that yields the x values, where y is equal to 0, also known as the x-intercepts, which we studied when we looked at linear equations in Math 145. The x-intercepts are often referred to as solutions, zeros, and roots. The methods we'll be solving quadratic equations with in this course are factoring as well as quadratic formula. And although we have various methods to solve quadratic equations, it's important to note that the solutions should all be the same if the method is carried out properly. Before we jump into discussing the methods for solving quadratic equations, I want to talk about what a quadratic function looks like graphically and what these solutions look like that we're talking about. Here we have the graph of y is equal to x squared minus 7x plus 12. We were asked to find the x-intercepts of this equation. That means that we want to find the values of x where y is equal to 0. Therefore, we're solving the equation x squared minus 7x plus 12 is equal to 0. Labeling our x and y axes, we can see where our graph crosses the x-axis at our x-intercepts. And by visual inspection, we can see that they pass right on the grid lines where x is equal to 3 and x is equal to 4. And we can list these coordinates as 3, 0 and 4, 0. Therefore, there are solutions at x equals 3 and x equals 4. We haven't looked at graphing parabolas yet, and in these notes we'll be looking more at parabolas as well as their transformations. But the way that you could have arrived at this graph is to either graph it using some computer software such as GeoGebra or Desmos, or graph it by hand using a table of values. Now that we have two solutions, x equals 3 and x equals 4, we can verify that they are in fact solutions by analyzing the equation algebraically by plugging in the x values into the right-hand side of the equation, and if they are in fact solutions, you'll find that the right-hand side of the equation reduces to 0. Therefore, the left side equals the right side, and they are in fact solutions. You'd have to check each of these x values separately, so plug it in 2 times. Now that we know the x-intercepts of this equation, we're going to solve the same equation by factoring. It says find the x-intercepts of y is equal to x squared minus 7x plus 12 by factoring. Recall that the x-intercepts occur when y is equal to 0. Now you may want to factor by decomposition, some other method, favorite method of factoring, but we can see that this factors into x minus 3 and x minus 4. Now we have the product of two numbers, so x minus 3 is one value and x minus 4 is another value, and the product of those two numbers can only equal 0 if one of the two values is equal to 0. Therefore, consider x minus 3. We know that that must either equal 0 or x minus 4 must equal 0. Solving this, we find that x is equal to 3 and x is equal to 4. Therefore, we're able to identify that the x-intercepts of this original equation are 3, 0 and 4, 0, as we saw above with the graph. just as a reminder, if you multiply factors and the product is equal to 0, then it means that one or both of the factors must equal 0. And that's a key point here. Anytime that you would like to solve a quadratic equation by factoring, you must first rearrange the equation to make sure that it is equal to 0 before you proceed with factoring. In a moment, we'll see some examples where we need to rearrange the equation before we solve for the values of x. Now some examples. It says to solve by factoring, we have 2x squared minus 8x is equal to 0. To factor the left-hand side of the equation, we can common factor out a 2x, and we're left with x minus 4 is equal to 0. If you still feel like you're struggling with factoring, you should go back to Module 4, try some of the recommended homework, make sure you attempt your quiz, and contact your instructor if you have more questions. There's a reminder here that we should not divide by a variable. So although both the terms on the left-hand side are divisible by x, you do not want to divide the left-hand side of the equation by x, or you will lose one of the possible solutions. So here we have the product of two values that are equal to 0, therefore either 2x is equal to 0 or x minus 4 must equal 0. Now solving each of these equations for x, we find that x is equal to 0 and positive 4. Part C, x squared minus 5x plus 6, we can factor that as x minus 3 and x minus 2. Therefore, we know that x minus 3 must equal 0 or x minus 2 must equal 0. And we find the solutions of this equation are positive 3 and positive 2. So as a reminder, we can take each of our solutions, plug it into our original equation, and we should find that the left side is equal to the right side if they are in fact solutions. Depending on your comfort with factoring, you may need to show some extra steps to solve a problem like this, and make sure you take the steps you need to complete it well and according to correct mathematical reasoning. For part C, we would like to determine the value of x that satisfies this equation. We're given 6x squared minus 11x is equal to 10. Remember, to solve by factoring, it hinges on us having a quadratic equation that is equal to 0. So we must first move the 10 to the left-hand side, or you could rearrange everything to the right-hand side such that your equation is equal to 0. Moving everything to the left, we get 6x squared minus 11x minus 10 is equal to 0. It's worth noting that if you were to move all your terms to the right-hand side of the equation, you would end up with the exact same solution as you will in this case. This equation factors into 3x plus 2 and 2x minus 5, and that's equal to 0. That means that one of those two factors must be 0. And we find that 3x is equal to negative 2, therefore x is equal to negative 2 over 3. Or 2x minus 5 is equal to 0, and therefore 2x is equal to 5, and x is equal to 5 over 2, or 2.5. Part D, we're able to solve this problem by factoring by grouping. As you can see, by grouping in pairs of two terms, we can common factor out of each grouping, and we have x multiplied by x minus b plus 3 multiplied by x minus b. That's equal to 0. This continues to factor. If we factor out the common factor of x minus b, we're left with x plus 3. And the product of those two factors is equal to 0, which means that x minus b is equal to 0, or x minus 3 is equal to 0. For the final solutions are x is equal to b and x is equal to 3. So you could substitute b in for x on the left-hand side of the equation, and you'll find that it reduces to 0, and likewise with x is equal to 3. Now we would like to solve the equation s over 3 is equal to negative 5 divided by s minus 8. Remember, we have a fraction that is equal to another fraction. This is similar to the proportionality problems that we solved in Math 145, and you can either clear the fraction by multiplying both sides of the equation by 3 multiplied by s minus 8, or consider it a problem where we cross multiply. And if we were to cross multiply, you end up getting s multiplied by s minus 8 is equal to 3 times negative 5. This reduces, or I guess you can expand it, to be equal to s squared minus 8s. Just as a reminder, I expanded the s into the brackets on the left-hand side of the equation. Now we have a quadratic equation. But before we can proceed with factoring, we need to make sure that we bring all the terms to one side of the equation. This is a factorable equation, and it factors into s minus 5 multiplied by s minus 3. Therefore, s minus 5 is equal to 0, or s minus 3 is equal to 0. Therefore, solutions are s equals 5 and s equals 3. Now we have two more examples where we're asked to determine the quadratic equation with the following roots, and we want to express our answer in the form ax squared plus bx plus c is equal to 0. In part A, we're told that the roots of the quadratic equation are 2 and 5. This means that our graph crosses the x-axis at 2 and 5, at x equals 2 and 5, for it would appear something like this, not to scale. Given our solutions of x equal to 2 and x equal to 5, we can write this as a quadratic equation where we have x minus 2 and x minus 5. Remember that the roots are the result of solving for the linear equation where we have x plus or minus a value is equal to 0. So now we know that this is equal to 0, and we can expand the left-hand side to put it into the equation ax squared plus bx plus c, and we get x squared minus 2x minus 5x plus 10 is equal to 0. And simplifying the left-hand side, we get x squared minus 7x plus 10 is equal to 0. Therefore, this is the quadratic equation with the roots x equal 2 and x equal 5. Next, we would like to determine the quadratic equation for an equation with the roots x equal 3, and they're real and equal roots, so two roots that are the same. We could express this as x minus 3 is equal to 0. One thing that we know is that our graph will look like the following. We have an x-intercept at 3, and our graph will either open up or down and have a single x-intercept at x equals 3. There are more than one equation that would satisfy these roots. We could add a stretch factor, so a different value out front of our two factors. For instance, you could place a 5 or a minus 2 or minus 1 out front of this expression, and it would still have real and equal roots that are both equal to 3, but this is one possible example. So here, if we expand out these terms, we get x squared minus 3x plus 9 is equal to 0. And simplifying, get x squared minus 6x plus 9 is equal to 0.